So I'll just give this introductory talk, and to set the scene, this is not a technical talk, so doesn't matter if people miss a few of the slides, I'll just get it over with. So I was very grateful that we're able to give this course. I'm not going to be giving any of the technical content of the course. The technical content of the course is given by people from the VI-HPS consortium who develop all these tools, so they're the experts. My role is really just coordinating some of the training on Archer. So I'll very briefly set this session in context. And okay. So this training is given under the umbrella of Archer 2. The Archer 2 is going to be the next UK National Supercomputer Service. It's going to be, I'm from EPCC, the Edinburgh Parallel Computing Centre. It's going to be a Cray machine, and we're going to run it here in Edinburgh, in Scotland. Of course, you may not even been aware that we're based in Edinburgh, because normally you'd have travelled here, but of course, in the current climate, we're doing it all from offices or homes. As part of running that service for Archer 2, and the machine isn't installed yet, it's been delayed for a whole bunch of reasons, such as COVID. We run 60 tech training days a year at various locations, but clearly now online. And this form is one of those courses. This is going to be the machine Archer 2. It's going to be a Cray Shasta system, quite a large system, 750,000 CPU cores. It's being installed at the moment. But actually, we're going to be doing the exercises on our current national supercomputer Archer, which is actually looking a bit old, but is perfectly okay for. And I'll give a very brief overview of what Archer looks like at the end. We also have another machine, Cirrus, which we use for some, has about 10,000 cores. Archer has about 100,000 cores. Cirrus has about 10,000. We use that for some of our courses, but not for this course. We felt Archer was the most appropriate platform. So what is EPCC? We're the closest thing the UK has to a national supercomputer centre. We've been around for a long time, 30 years or so. We're part of the University of Edinburgh. And we have over 100 full-time staff. We do a range of academic research and commercial projects, including postgraduate teaching and HPC training courses. And the reason I mention this is that if you want to collaborate, if you come away from this course thinking that was really useful, I could use those tools on my own codes and help develop my own parallel simulations. If you want to collaborate with us, and you can collaborate with any of the people who are giving this course, I'm sure, but you can. We operate very much as academics, research associates in terms of research grants, because we're part of the University of Edinburgh. You won't need these Archer 2 resources. We're running the course on Archer, and I think that the presenters have tried to kind of shrink wrap the exercises they just run. But there's a lot of material going up about Archer 2, but that's not relevant for this course. Who am I? My name is David Henty. I'm an overall charge of education and training at EPCC, although actually the Archer 2 training program is run by my colleague Juan Herrera, but he's not available today. He has other commitments, but I happen to have overall charge. That involves this training for Archer 2, but also the MSc. We're a PRACE training centre, and we do some commercial training. In my own work is sort of around performance, new parallel programming models, accelerators, and performance. And that's one of the reasons I'm interested in tools, because whenever you start talking about performance, you need to understand, if you want to improve the performance of a program, you need to know how it's performing at the present time. And with the complexity and size of modern HPC systems, that's almost impossible without good tools. There will be a feedback form. Please fill in the feedback form. You will get some reminder emails about it, but it's very important. We do take feedback seriously. We review the feedback at weekly meetings. As I always say, good feedback is great. It makes us feel good about ourselves, and we can tell EPSRC how wonderful we are. EPSRC is the Engineering Physical Sciences Research Council that funds the major supercomputers in the UK. If we get poor feedback, that's equally important, because we can then act on it and make sure that the courses are more relevant in the future, or that the technology is better, or whatever. We run an MSc in HPC with data science. I won't plug that too heavily at the moment, but I normally plug it to people. Just quite proud of our MSc. We also run a MOOC, a massively open online course. I don't think that'll be relevant to the people attending this course, but maybe your colleagues might be interested, or you might have people who want to learn about HPC. It's part of the supercomputer, the FutureLearn platform. You can do it for free. They try and get you to pay a bit, but you can do it all for free. We have run it 5 times in a collaborative way. It's currently now available in the self-study mode. So there isn't any active support from EPCC educators, but there is a community of people doing it. And you're welcome to join that course. It's still available, and you can look at the material and follow that on. It's completely conceptual, so it's really an introductory course, but hopefully interesting. During the course, you have personal accounts for the duration of the course. The access will be there for maybe up to a month afterwards. Before, up 2 weeks after the access ends, the accounts will be closed and files will be deleted. So take copies of all your work beforehand. But don't worry about the material, the slides, the exercises. We'll put them all up on the Archer 2 website. So the only worry you have is if you develop your own code or your own files on Archer, you want to copy them off. But you will have these accounts, I believe, are going to be open until the end of August to give you a chance to carry on and do work after the course is finished. Longer term, there's a number of ways you can apply for access to Archer or Archer 2. There's obviously requirements about what research you do and whether you're a UK citizen or European. But we hope to have a driving test available. This will be a way that people can get access to the system by answering a few multiple choice questions. This is all in the future, of course, because the Archer 2 system has been delayed. If you're interested in our training program but not interested in the entire service, maybe not going to be an Archer or Archer 2 user, but all our training is available for free. You can subscribe just to the training email. So that might be something you might be interested in doing. This is not relevant. We can't guarantee the security of your room. I don't know where you're training from, but we normally say we can't guarantee the security of the training venue. It's not relevant at the moment. We have a code of conduct. Please look at that. We just expect people to be basic, obvious things: welcome and inclusive, be respectful of people, accept constructive criticism, focus on what's best for the community, and be courteous and respectful to other people. I'm sure everyone will abide by those, but I just wanted to put that up. It's something we expect people to have in mind. And this isn't relevant. Well, it is actually. If you're a UK user, you can apply for funding on Archer 2, which isn't there to fund CPU time or scientific research. It's there to fund software development. It's called the ECSE program, and this is there to allow researchers based in the UK. It's a UK funded service, although we have users obviously from all over the world, to employ somebody or get a postdoc or a researcher to work on a piece of software for an extended period, 6 months, a year or so, to make it more powerful, more functional, more performant on a platform like Archer 2. That's the ECSE call, and there's regular announcements of that. This course is also part of our PRACE. We're a PRACE training centre under the Partnership for Advanced Computing in Europe. We are still, despite the UK's status in Europe, we're still members of the current PRACE project. We will be at least until the end of PRACE 6 IP. So we run training under the PRACE banner, and this course forms part of that training program as well. There are 10 PRACE training centres around Europe. Currently, obviously, on-campus training has been suspended, but a lot of these centres are delivering online training. So if you're interested in what training is being offered by the PRACE training centres, there's the URL training.praceri.eu, and that will list all the current training provision of all these centres. PRACE, well, normally it funds catering and other expenses. That's not relevant here. But as I said, those are the URLs, and the feedback is a PRACE feedback form. Finally, I'll very briefly go over what the Archer hardware and software setup is. There's 4,920 nodes with 24 Intel CPU cores. They're relatively old CPUs, but fairly standard. In terms of the exercises, you get batch access via PBS Pro, which uses QSub. I know most people are moving to Slurm now. We are definitely on our systems, but Archer is still with PBS Pro. The things which might catch you out are you have 2 file systems. When you get an account in Archer, you have 2 directories: a home directory, which for this is in home TA002, TA002 username, but also an equivalent work directory. And one of the idiosyncrasies of Archer is you must run all parallel jobs from /work. So my recommendation is, as soon as you log into Archer, just cd to /work, because there's no real reason for doing stuff in /home for the moment. So Geert has said that my list of PTCs is somewhat out of date. It might be, yes, apologies. That could be out of date. I updated it from the original 6, but I apologize if I've missed anyone off that list. I should check that it's more up to date than that. Apologies. And we will have reserved queues for each day for fast turnaround. Today, the queue is R7133965. That I'm sure the trainers will have a note of these. You'll be able to use your account anytime when it's active for the next month, but you would just have to submit to the main queues, in which case you're competing with lots of other users and it might take a long time for your job to run. That's clearly not ideal for a training course. So we have these reserved queues, and there's a different reserved queue for each day, but that will add something like 30 or so nodes, 700 or 800 CPU cores, which will give you fast turnaround. And general, I hope you enjoy the course and please ask questions. Most people find it easiest to ask questions in chat. You can use the audio if you want, but the chat probably works best. And the presenter will, I think, get an audio notification of a chat message. So that it's up to you, but I think that chat is often the best way to raise a question. If there are issues which require hands-on support, we can try using the breakout room facility of Collaborate, which allows you then to share your screen in a private, secure way with a trainer, but we'll have to see how that goes. So that was really all I had to say, and I just wanted to, I hope everyone enjoys the course, and pass on to the first speaker who will give the more interesting technical talk. I would just say that if you've, unfortunately, getting an account on Archer is slightly more complicated than it used to be because of a lot of, there were worldwide security incidents recently in the last month or so, which affected a whole bunch of systems worldwide. We've had to introduce extra security measures, so our logging in procedure isn't as seamless as it used to be. If you are having problems, just email me. You'll have had emails from me already, d.hendy. Just email me and we can try and get them sorted out. Can't guarantee to get you an account immediately. There are some manual steps, but we should be able to get you an account, you know, if you start applying this morning, maybe this afternoon, definitely for tomorrow morning. For non-UK people, there are unfortunately a couple of extra by hand steps which we need to do. But I do see that some of you have managed to get accounts. So that's really all I had to say, and I'll stop sharing, and I will pass over to Cedric Valenci, who's the main organizer of the course from the technical side, and ask him to start presenting and give the interesting material.
Thank you, David. Good morning, everyone. So I'm Cedric Valenci. I am an expert engineer working at the University of Versailles, and I am also the coordinator of the VI-HPS training program. So I will first start sharing a brief overview of the agenda of this workshop. So welcome to the 34th VI-HPS Tuning Workshop. Actually, this is also a first because this is the first VI-HPS Tuning Workshop that we're organizing online due to the restriction brought by the COVID-19 pandemic. So I hope everything will work all right. So this morning you have already had the welcome talk by David. Next, I will present briefly an overview of the VI-HPS consortium and the tools that are inside this consortium. Then I will present an introduction to the concepts and issues of parallel performance engineering. And then Brian will present you how to run and compile and execute benchmark on the Archer system, and we will use this benchmark afterwards during the hands-on for executing the tool, demonstrating the tools. After that, we'll have a break, and then we'll have a presentation by Judith and Lau from Barcelona Supercomputing Center on their tools. And after a lunch for break, you will get a coaching from BSC, or how to use BSC tools on codes. So one point I will just one quick show of hand I would like to have right now. Who among you already has a code that is running on Archer? You can use the raise hand functionality on the bottom of your screen if you want. Okay, so I see one code running on a. No, I don't. Okay, so no, nobody has any code actually running on Archer, right? Okay, one code. Okay. So normally during the VI-HPS workshop, we focus on. Thank you. We focus on helping users with their own code. Due to the format of this workshop, will be mainly demonstrating the use of the tools through tutorial sample benchmark codes. But for the people among you who have a code already running on Archer, we'll be happy to help you with your code. So the last, returning to the agenda, the last presentation of the day will be the TOE performance system by Samir from University of Oregon. So the presentation is in the evening to account for the difference in time zones. Tomorrow, the full morning will be held by Brian and Christian. Will present you the Scorpy, Scalaska, and Cube ecosystem from GSC, and you will get to apply them on code in the afternoon. Please note that due to some time constraint, tomorrow afternoon session will start a quarter of an hour earlier, and the break will be a quarter of an hour shorter to account for some time constraints. And once again, in the evening, we'll have coaching for using TOE on codes, the TOE tools. On the last day of the workshop on Thursday, the first slot of the morning, we'll have a presentation of the Macao tool from the University of Versailles, and the coach followed by the coaching on how to use it to analyze codes. And in the afternoon, a presentation on of the ARM map and performance report tools, and followed by coaching on how to use it on codes. And we'll conclude with a short review of the workshop. So we'll now present the VI-HPS consortium. So VI-HPS stands for Virtual Institute High Productivity Supercomputing. Its goal is to improve the quality of high performance codes and help developers to accelerate the development process of these codes and to obtain the best performance of the current systems. So it's now, I think the consortium as it is now is 13 years old. We focus on developing HPC programming tools, focusing on correctness checking and performance analysis, and in order to maximize the performance of application. And then we propagate the use of these tools through academic and training workshops such as this one. And we have a website where we aggregate all the information on our tools and the training events you may want to check it. The VI-HPS consortium was initially founded by the Jülich Supercomputing Center, the RWTH Aachen University, the Technische University Dresden, so that's 3 universities in Germany, and 1 university in the US, the University of Tennessee in Knoxville. And these original partners were joined by a lot of different partners from various universities and companies across the world. We recently welcomed ARM, There is the Barcelona Computing Center in Spain, Lawrence Livermore National Lab in the US, the Leibniz Computing Center in Germany, and Technical University of Darmstadt in Germany. We also recently welcomed the Erlangen University, the Technical University of Munich in Germany, University of Oregon in the US, University of Stuttgart, and University of Versailles in France. So we have built a large portfolio of tools, some of which will be presented to you during the course of this workshop. We regularly publish a tools guide on the VI-HPS website. It is updated around twice per year, so you can get all the information of the latest tools that have been added to the VI-HPS tools portfolio. So all our tools focus on correctness and performance, but they all focus on different points on the issues. We have tools for correctness checking and interfacing with the performance counter. Scala-SCA is a large-scale parallel performance analysis tool. So an integrated parallel performance system. There is a Vampire that performs trace analysis. Scorpy, which is a measurements infrastructure. Also the Forge tool suite on profiling and performance report and parallel debugging. Tools for modeling cache and performance. We have also some tools that are not directly associated with performance analysis, but help streamlining the process by streamlining the workflow of execution. We have also tools for performance analysis and optimization, like Macao. Other tools that are more focused on MPI interface, MPI profiling. There is the BSC tool suite with event tracing and visualization of analysis of trace, and other tools for analyzing parallel and parallel I/O and stack trace. So this is a brief overview of how these different tools interact with regard to the general optimization process. So it's a circle because optimization is a never-ending struggle. So whenever we have reached a certain level of optimization, we want to start tackling on the next bottleneck. So the idea is that we may start with executing and, of course, making sure that our application is executing correctly. So for that, we'll need some debuggers tools and memory checker. Once the application is working correctly, we may want to see how well it uses the machine characteristics. So that's where we'll be using hardware counters and cache simulation. Then we may want to profile our application and see exactly what's going on inside it using some profiler and trace collection to see exactly what's going on. And then once we have collected all these traces, we want to analyze them to derive some optimization hints and apply them. And once we've reached that point, we can start for another round. So you can see in bold are all the tools you will be presented during this workshop. So the Forge, Mapira, and then Macao are the profiling and tools. So Scala-SCA, Scorpy, Extrae are profilers and trace analyzer and prover, and also Macao can provide optimization hints. So one point we want to make is a tool is not a magic wand that will automatically make a code more performant. It will, however, help you, the developers, by pointing out what can be done to improve it, and hopefully allow you to reach an optimal performance of your code more quickly than by simply trial and error. The VI-HPS also organized, so I talked about the training and tuning workshop. The goal is to provide an overview of all the tools and how they interact with each other and how they can be used to tackle different aspects of the performance engineering issues. The idea is that we can, during this workshop, we want to show what these tools can do, how they can help you to do, how they can help you to improve your code, and directly allow you to use them, if possible, on your own code and see how they can help you to improve them. One point that is also very important for us is to obtain feedback from you on our tools. This also allows us to improve them and address some issues and guide us in our future development on our tools and on the organization of this training workshop. So by the end of the week, you will also receive a link to an online form, an evaluation form of the workshop, where you'll be able to evaluate the different tools that you have been presented and what you thought of them in the workshop as a whole. So please fill this form, because it's also important for us to allow to improve our tools. So usually we have 2 or 3 workshops per year. In blue are the workshops that were part of the PRACE training program. We also have some tutorials that are organized at international conferences like Supercomputing and ISC. Obviously, this year, this agenda will undergo some changes due to the various restrictions from the COVID-19 pandemic. And just an overview, we have been organizing this workshop in various locations in Europe, in Germany, the UK, France, Spain, but also some of them are organized in the US, in Japan, or in Chile. Of course, starting now, the actual location of the workshop is not that important, but hopefully in the next year or so, we'll be able to have live workshops again. So some incoming events. So we had once again to postpone some workshops originally scheduled to take place in April and May. So they have been pushed back to rescheduled to this fall. We should have a workshop organized by HRS in Germany that will also take place online, and that will take place in September. A workshop organized by Shineka that should take place by the end of this fall, and will also take place online, and a workshop that should take place in Frankfurt, Germany. So right now we are not sure whether it will be a live workshop or an online workshop. In any case, all future events will be announced on the VI-HPS website, and any change or update will be announced. So if you are interested, you can always check the website to get the latest news on our training program. And of course, if you yourself are interested in hosting a training event in your organization, you can also contact us. We are always eager to find new venues to organize our workshop and new system. So this was an overall presentation of the VI-HPS Consortium. Now we'll enter the meaty part, which is exactly the main principles behind parallel performance engineering. Some of them might be already familiar to you, but they are important to envision over the course of this workshop. So performance is an old issue. You can say it's as old, if not older, than computer science itself, since Charles Babbage was already aware of this issue, and he was working on a mechanical computer in the 19th century. And by the way, the analytical engine which he developed was already included some concept of parallelism to be able to allow some cylinders to work on a problem while they were idle. So this is not something new, and it's still not solved, but we're working on it. So the main issue is that the golden age of computing is gone, and now we simply can't double the power of our computer chip to divide the execution time of an application by 2. Sadly, now we have to take into account that the power of computer chips are mostly obtained through parallelization, and simply increasing power is not profitable anymore. So this means that parallelization is another issue to tackle, and we also the computers are becoming increasingly more complex, which makes optimization increasingly complex in turn. There are different factors that could impact performance. First, computation itself. We have to make sure we have been able to find the right algorithm for the right problem, and that the compiler is your friend, but you have to know how to use it. So that's important to be able to use the right flags of compilation. Then there is the use of memory. Computer now include different levels of cache to be able to optimize access to memory, but this is a very tricky problem, and we can never be sure exactly what is being done with memory, and it's very important to take into account. And there are, of course, the I/O problem, input and output of programs, which can impact performance and may be overlooked because we may not pay attention to what's happening during initialization of a program. And of course, these were the sequential problem. Now there is all the issues brought by parallelization, which is correct decomposition and partitioning of a problem. How to optimize communication. We don't want to have all our processes constantly exchanging messages. Same to how to optimize the threading. And of course, there is the problem of sharing resources and to avoid locking. So the idea is that the goal of the key to performance is be able to correctly balance the right libraries, the correct algorithm to use, and find out the correct compilation flags and directives. And what's also important is that performance can be counterintuitive. And so just by looking at the code, even if we think it is optimized, it may not actually be at all. So it's better to actually really be using a tool to check what is going on and whether we actually did actually optimize our code as best as we thought it is. So that's why it's better to be measuring, to be able to identify the performance bottlenecks, because they are not always where we think they are, and to validate after each step of optimization, because if we optimize a lot of things at once, we may not be able to identify exactly what went on. So how does performance engineering work? So once again, it's a circle because we keep improving and over improvements. The idea is that we will start on the bottom, the top left here, and first point is that we may want to prepare the application to be monitored, and then we collect the data that has been generated that way, analyze it to derive some metrics, and identify the issues, the performance issues of the code, and then derive some hints and advices on how to improve performance and integrate them. And once we've reached that point, we can go on to tackle the next performance issue. One important point is that we don't want to spend all our time improving performance. The idea is that we also want to focus on the biggest issues and also those that will yield the better speed up, because it may not be always interesting to focus on the biggest bottleneck if we can identify that they will not bring as much as we hope. And there is a point where we'll have to know where to stop, because if we can identify that we only gain a few percent, maybe it's not worth the hassle to be working days and days to gain another percent of performance. So across this workshop, you will see the tools collecting and manipulating different metrics. So that's a definition of what we will be using. Count will be counting how many times a given event occurs. That might be, for instance, the number of messages sent, the number of calls of a given function. Then there is the concept of time, of course, the time that we spend in a function, the time that is spent between two MPI calls. And there is the problem of size. What is the size of messages exchanged? What is the size of the footprint of the application memory? And from all these metrics, we can also derive other metrics, for instance, dividing a number of events by time, or the size by time to normalize them and obtain rates or throughput values. So, for instance, I already mentioned them. We can consider execution time of the application as a whole, or for a given function. The number of calls of a given function, for instance, some MPI primitives, the number of cycles per instruction, and one metric that you are probably already familiar with is the floating point operation executed per second, which is traditionally used to characterize the power of computer. Of course, that's already a question to know exactly what we consider being a floating point operation. Is it just a mathematical operation? Is it the number of hardware instructions? Because sometimes a given mathematical operation may be translated as a single, as different hardware instruction, or conversely have multiple in a mathematical operation become a single instruction on the computer. So we have to distinguish, when considering execution time, the difference between wall time, which is basically the equivalent of starting your timer, launching your application, and stopping your timer when the application stops. So the point to consider is that while it gives you actually really the time that you spent executing your computations, it's may not be exactly identical to the time that the machine spent working on your problem, because there may have been some context switching between different tasks already executing on the computer. So that's why we also use the concept of CPU time, which is the time actually spent by the CPU to execute the application. So that may not always include the time where the application actually sleeping at some point or waiting for something, and during that time the processor the CPU will not be actually working on it. One point about time is that it is non-deterministic because all of this. So in a perfect world, of course, in a perfect environment only dedicated to executing only one application, maybe we could hope for a deterministic time, but most of the time we can have sometimes wildly different timing between two execution of an application. So that's why usually it's better to perform different measures to obtain a means or minimal or different ones to be sure that, for instance, we have obtained a speed up after implementing a given optimization. One point to consider about one word that we'll see keep coming in the different profiling tools is inclusive or exclusive time. Inclusive time means the whole time spent somewhere from start to end. So for instance, here, if we are considering the inclusive time spent in function foo, that will be the whole the time counted from the entrance to the function to the exit from the function. Conversely, the exclusive time is the time spent only in that function and not, for instance, in a function that it invoked. So for instance, in this case, the exclusive time is only the operation that were performed by function foo itself and not whatever happened in function bar. So both of these type of values are useful, whether you want to see, for instance, what is the most costly function or where do we take the most of time. So the various tools that you will be presented use measure what is going on inside an application. And there are different methods to measure this and to aggregate values and analyze them. So we'll see here now an overview of the various methods that are used for these and their pros and cons for each. So one of the methods for measuring events in an application is sampling. Basically, this is the equivalent of executing an application in a debugger and periodically stopping it to see what's going on and where we are. At regular interval, sampled application will stop it, check where is it, in which routine, which function, what is the context, and let it continue. So one advantage of this method is that it is minimally intrusive because we usually don't need to modify the application to perform this. And it also yields a rather low overhead on the whole. So the application will not be too much slowed down by the sampling process. Conversely, the drawback is that it is a statistical method. So you will only get statistical values of what's going on, which means that a very short event, for instance, could be skipped. So here, for instance, if you see what's going on between the T5 and T6 indices, you will see we're spending some time in foo1 and main, but that will be lost. So we won't be able to get a precise mapping of everything that went on during the application execution with sampling. And of course, because it is a statistical method, we will also need a long-running application to obtain a significant value. Long-running is in computer terms, so that's something that at least a few seconds, but still, that means it's something to keep in mind when using sampling. Conversely, instrumentation. So instrumentation is something you have probably all done at some point of your developing career. That's basically the equivalent of inserting a print command somewhere in your code and to see how many times it's printed because you want to see what's going on. So instrumentation is this ID. Basically, we'll be inserting probes at different points of interest in the code, and we'll be getting whatever these probes record. So the advantage of this method is that we can obtain precise information of what is going on inside the application, because we can get as precise information as we want. We just have to add more probes. Of course, the drawback is that we are adding more probes, and so these probes may significantly slow down the execution of the application. And the more probes we add and the more work they perform, the most important the slowdown is. Another problem is that requires us to modify the application. So it's a bit more complex to put in motion. So there are different techniques of instrumentation. The idea is that either we will modify the application once and then execute it, or there are some tools that allow to modify it while it is being executed. And so we can instrument an application manually. So that's what I spoke about, was saying you simply add some prints into the code, or you can have different automatization methods to instrument it. So there are some source-to-source transformation tools, like Scorpy, for instance, or you can use a compiler to the compiler. There are some already integrated compiling modes when you can ask the compiler to actually insert some probes inside the code. You can also modify directly the binary code itself. That's what's done by Macau. Or also override the use of external libraries to force the use of instrumented libraries to obtain what you want. So one issue of instrumentation is that we are modifying the application. And so since we are modifying the application to insert the probes, we are also modifying its behavior. So the issue is that we may be actually modifying what we are trying to observe. And so what we are observing is not the actual behavior of the application without instrumentation. And of course, there is the issue that the probes inserted themselves may also significantly impact the execution of the application. So that's why it's useful when using instrumentation to know precisely what we want to observe, and possibly instead of performing one big instrumentation where we want to obtain everything, perform more focused observation that will provide exactly the information we need with minimal overhead and impact on the application behavior. So now that we have seen how to produce data, we'll see how to record it during the execution. So we can record aggregated information. So just check we can obtain a summary of the measures we generated. So for that, we will record, for instance, aggregate information to obtain only a count of values or total of maximum, minimum, time spent somewhere, time spent in some parts of the application. So basically, a profile is just a summary. You will get to see what happened in the application, but there is no time scale element present in a profile. So we can have a flat profile where you will see exactly everything that went on, but without calling context. So you will see what was spent in the parts of the application, but will not get the information of which part preceded which other part. Conversely, the call path profile will try to stick to the actual code graph of the application. So you can see exactly, for instance, in a call path profile, which function was branched from which other. And you can also have different profiles focusing on specific parts of, for instance, MPI call of MPI messages, or the life of threads across the application, the life of the application. Conversely, tracing will try to stick to the temporal. We'll add a temporal component to the data aggregated during profiling of the application. So we'll be able to see exactly the relative timing of the different events which came first. So each event will be chronologically timestamped. And a tracing profile allows you to exactly see what went on as time went on inside the application. So here is an example of a tracing report. Let's suppose we have been instrumenting these two processes, A and B, to check where we enter inside functions and the messages that each of them are sending and receiving. So each of these, we generate a trace with a timestamp describing what happened at a given time inside the process. So one point here is that for this to work correctly, we need to be able to be sure that the clocks for each processes are correctly synchronized, so that the timings of both traces are coherent. And if we have both of these, we can merge those and see exactly what went on between both threads across time. So we can see which function enters first, what happened, that we sent a message first, and that it was received afterward. So this is what a tracing profile will provide you for more information. So the advantage of tracing is that as you can see, we can see exactly what went on inside the application across time. So we can know exactly where we spend time, and this is very important, for instance, in parallelization, because we can see if there was a process that was waiting for the other to complete, or one that was hogging the most of the computation itself, whether there was a different behavior of the application depending on whether it was in the initialization phase or the computation phase. So this can provide the most accurate information. Of course, the drawback is that timestamping everything that goes on inside the application can lead to huge traces and even a huge overhead during trace collection. So this is a powerful technique, but it's necessary to be able to know where to use it, when to use it, to avoid generating too large traces and to slow down the application too much during its execution. So now, what do we do once we collected this data? So one first approach is to analyze the data as it is being collected. And this, for instance, allows to modify what is being collected during the life of the application. But of course, it requires a formalized knowledge about performance bottleneck, and we can implement more sophisticated interprocess analyzing with different techniques. The other type of analysis that is most commonly used is post-mortem. That is to say, we'll generate all these traces, and then once it's done, we'll aggregate them and either aggregate them just like we saw in the example before, or perform some statistical analysis. And we can also generate some visual traces to be able to see humanly what is going on. One example of this, for instance, so using the traces from the previous example, how we could generate from this something that can be that allows to see quite easily what went on in the application. So here we simply represented on this visualization where we were at different points of the application execution and the messages that were exchanged during the life of the application. So this allows to quickly get a view that at a glance allows to see what went on. So the point to keep in mind is that after we have seen all these methods, there is no golden method, sadly. And it's not possible either, it's not very recommended to decide to turn all the knobs on and gather as we want, and because it may impact the application too much. So the important thing is being able to correlate all these methods together, to combine the tools and the methods to obtain different and complementary information. For instance, we can have different type of analyzing or visualization of measurements, and by correcting all of them, we can get an optimized view of what's going on, and with a minimalized overhead. typically, what are we going to ask ourselves when we want to analyze something, and what do we want to do? Which tool do we want to use at which stage of the analysis process? Of course, the first question is, do we actually need to improve our performance? So that's easily done by measuring time of the application and see if we have the application and see whether we are satisfied with it or if we want to improve it. Whether the scalability of the application is satisfactory or not. So we'll have to perform, for instance, multiple runs of the application across different scalability configuration and see exactly how well it works. Once it is done, we may want to understand whether the problem lies in computation or communication. So for that, we'll monitor MPI or OpenMP runtimes and see how the application uses them, or profile the application to see exactly which function are taking the most of the time. Once this is done, we want to know where is the bottlenecks. So for that, we'll perform more detailed profiling into the area we have already identified. And once we have it, we want to know why is this a bottleneck. So we'll delve deeper, for instance, for either we can trace a very selected part of the application where we have identified that the issue lies, or perform some hardware counter analysis to see exactly why this part of the application is not behaving as we want. Another issue is to see, is the application using parallelization correctly? So for that, we'll want to trace, analyze imbalance of the application, or compare the different processes and threads behavior to see exactly how well they're working with relation to each other. So of course, all of this procedure will something, the tools that you will see during this work will allow you to illustrate some parts of this procedure. And the idea is that an aggregation of all of them will allow you to take the best advantage of the machine capacities and the optimization of your application. So this was a broad introduction to parallel performance engineering. Now I will leave Brian Willey present you the how to use Archer to execute a benchmark that we'll be using for during the workshops as a tutorial to use the tools on. I will stop sharing now.
Okay, so I'm Brian Wiley, and before we move on to actually using the tools, I wanted to take this opportunity to just briefly familiarize with how you build, run things on the Archer system. And so for that, we have a short exercise, a small example program. It's actually a benchmark that runs on a wide variety of systems. And that's an opportunity just to have a common application in which we can apply the different performance tools to. You're not expected to really understand the application, or certainly not to do any tuning of it, but just to see how it executes and what you learn from applying the tools to its execution. I understand that most of you are not familiar with Archer, so we'll see how this goes. Typically, we would do this by switching back and forward between the slides which I'm going to present and showing things on a terminal session. What I propose to do this time is just to run quickly through the slides, and then I'll switch over to the terminal session, run through things again, and then at your own time during the break or in the afternoon session, you can find these slides. The slides are available on the VI-HPS website, and then go through the instructions at your own pace just to make sure that you understand how to do things yourself. And that will set you up for being able to apply the other tools where you'll need to do a little bit more just than building and running the application itself. So the application, so that's the objective of this exercise, is just to have a base point so that we can familiarize with the use of the different tools that you'll see this afternoon, the rest of this morning, but also in the following days. It's a small portable benchmark code, so it's already running on a wide range of systems. It's also fairly well optimized, so you're unlikely to see major optimization opportunities in it. But it's a good starting point, and it's a good reference point for this exercise. And it's also a starting point if you wanted to try out different things yourself by comparing different compilers, comparing different MPIs. There's all sorts of binding and other placement optimizations you might want to look into, not necessarily on Archer, but on the systems that you're particularly interested in. You can look at the scalability aspects, how the performance changes as you increase it from 1 or 2 compute nodes up to 10 or 100 compute nodes. It's a very flexible, very malleable application here. And you can also use it to compare executions on different HPC systems. So you could compare Archer with Archer 2 when it's available, or with the systems that you currently use for your application development and work. I'm assuming that most of you, if not all of you, already have access to the Archer system, and that you'll be able to connect into Archer. So the command that you'll use is something like SSH for secure shell access to Archer login nodes with your user account. Since we'll be using some of the graphical tools, not necessarily today, but also later in the week, you might also want to enable X forwarding through the -X flag. If you're using PuTTY or one of the other tools to access Archer, then you'll need a slightly different setup, but basically an SSH connection to your existing account with X forwarding enabled is what we'll need. Once we've logged into Archer, you'll find that the default programming environment that's available there is the Cray programming environment, the Cray compilers, and the Cray setup. That's a fine environment for the Archer system, but if you're not using Archer, or if you're using other systems, you're probably more familiar with GNU compilers or Intel compilers. And therefore, for this exercise and for the other exercises that we'll be doing in this workshop, we recommend switching to the GNU environment. That sets up the GNU compilers so that things will be a little bit more familiar to you. We've provided a set of tutorial sources that you should work on. As was said earlier, you should copy these sources to your work directory. That's your user directory on the work file system. It may not already be set up for you. You may have to create it first. If not, just copy the files there, because you'll need things in that directory when you are running things on Archer. It's not mounted, or the home file system isn't mounted on the compute node, so you won't be able to see any files that you have in your home directory when you're running things on the compute node. So that's why we'll be using the work file system. We'll untar the star file, which has the sources in it. We'll cd into the directory that's created, and in that directory we'll see the sources that are provided for this benchmark. This box in the center of the slide here shows how that directory should look like. It actually contains multiple subdirectories for 3 different benchmarks. We'll be working with the one that's called BTMZ, but there's a couple of other ones there. Again, you could experiment with those later if you are interested. They're all Fortran benchmarks, which might not be your language of choice, your language you're most familiar with, but the language is actually not so important here. The application is built to use MPI and OpenMP, so it's a hybrid combination of MPI and OpenMP together. That's a fairly common setup, but if you're only used with MPI, that's fine. You just ignore the OpenMP parts of it. If you're familiar only with OpenMP, you should also see what looks like a familiar set of parallel loops and OpenMP constructs inside those. So that gives us a certain amount of flexibility. Hopefully it's relatively easy for you to follow. And as I said, we'll take you through the different steps of building and running this benchmark in a few moments on the Archer system. Just typing make in the base directory will give you a basic set of commands that you can use for building it. As I said, we can choose different versions of the benchmark. We'll be using BTMZ. The benchmark comes in different sizes, from very small sizes up to very large ones for for benchmarking of large configurations. We'll use something that's suitable for a couple of compute nodes here. That's the class C, and we'll build it with 8 MPI processes. We can control the number of OpenMP threads dynamically, but we need to build the benchmark with the number of MPI processes. And so there's a command that's on the slide here that is used for that. There's also a shortcut. If you use build suite, it will just build this configuration by default. Before we actually build it, I wanted to point out that we've set it up for the GNU environment. As I said, if you were to want to switch to one of the other environments, the Cray compilers or the Intel environment, they have different compiler flags, and so you'd have to adjust the make def. This is the configuration for the benchmark build in this directory, and then we would uncomment whatever line is relevant to the compiler we're going to be using. The compilers on the Cray systems go under generic names. So FTN is the Fortran compiler, irrespective of which compiler you're using underneath. We'll be using gfortran underneath, but FTN is the Cray compiler Fortran interface, the Fortran wrapper. And so by using that, it automatically will link in the appropriate libraries that it needs for that environment. If it's a C application, you just use CC or capital CC for C++. So there's some configuration here that I'll briefly show you, and you may need to adjust it if you're using a slightly different environment. As I said, make suite or make BTMZ class C nprox equals 8 is the configuration that we're going to choose to use. When we run that command, when we run make suite or when we run this make command, it will go through the source files, compile them with this Fortran compiler. It's using O3 optimization here, and at the end, it's also using, sorry, I should point out the OpenMP flag for the GCC compilers, -f OpenMP. So we're building everything with the GNU compilers in the Fortran environment with OpenMP support, and it's going to put the resulting executable into this directory here. It's a separate subdirectory bin where that executable is going to be stored. And if you were to use different build configurations, you could build with different numbers of processes or different classes, which would be separate files, separate executables that get built and put into that subdirectory. This application, this benchmark, is running a solver, a block tridiagonal solver for the Navier-Stokes equations in 3 dimensions. It's going to perform 200 time steps of this solver on a regular 3-dimensional grid. And as I said, it's implemented in around 20 or so source modules which need to be compiled and then linked together. When we're running in the configuration that I'm going to show you with 8 processes running on 2 of the Archer compute nodes, where each of the processes has 6 OpenMP threads, we should find that it runs in well under a minute. It should run in about 20 seconds in the GNU environment. Some of the other environments, it might run a little bit faster or a bit slower. This is something that you can experiment with, but if it runs in 20 seconds, it's a convenient test case for us to experiment with. And then we'll provide you with examples of the job scripts that you can use to run it on Archer. When you submit that job script using qsub, we'll see some output from the benchmark when it starts. We'll see it run through the 200 time steps, and then at the end we'll see it reports how long it takes to execute. And as I said, this will be between 20-30 seconds is what I would expect in the environment on Archer. So those slides, which I've just quickly scanned through, you find on the link that David just sent you from the VI-HPS website. And what I'm going to do is now start up a terminal session and then run through things so that you see things live. And I hope that this will also work for you as well. So I need to start up my screen here. Okay, so do you see my screen? Okay, I think you should be able to see it now. So what I've done is I've done an SSH at the top here into my account on Archer. You, of course, have your own accounts, and you'll need to put in your password or whatever to get into the system. That will put you into the home directory, but we're going to be working in the work file system, so I'm going to CD to the work directory. That's work TA002 again, and then your user directory if it's already existing. If not, you'll need to create it first. I have some stuff here that is from previous attempts working through this exercise, but I'm going to copy the tarball that we referred you to. It's compressed tarball, so I'm going to uncompress it as well. It's in the shared directory on the Archer file system, which you should all have access to. There's a tutorial subdirectory, and then these are the benchmark sources. So that's the only contents of that directory at the moment. So we should be able to just untar that, and then we'll find that we have a new directory that has been created here, and we'll CD into that directory and find what we have as the different source subdirectories that we were working with here. Before I get too far ahead and actually go in to build it, let me just check the environment that we have. So the default environment is the programming environment for the CRAE compilers. As I said, I would prefer to encourage you to switch to the environment for the GNU compilers. So I'm going to switch from CRAE here to programming environment for GNU. Now, when I do a module list, I should see that I have the GNU compilers. And if I wanted to check this, I can do cc version, and it should confirm that I have the GCC compilers, in this case the C compiler, as my default compiler. So that's the way in which this benchmark is set up, and which we encourage you to use. If I quickly show you the config file that I referred to, at the top of this file is where we have the different options for the different compilers. One is for the CRAE compiler environment, one is for the Intel compiler environment, and the one which is currently uncommented and the one which is the default, the one which is recommended, is for the GNU compiler environment. So this is the OpenMP flag for the enabling OpenMP in the GNU compilers, and then there's some other flags that are specific to building with that environment there. If I quickly go back here, if we scroll down further, we'll see that those flags are used when compiling. The default compiler is FTN. That's the one that's going to be used for compiling the sources, and that compiler flag is passed somewhere a little bit further down. Down here with O3 and with -G, some standard optimization and debugging flags. Okay, so as I said, if I just type make here in this base directory, it will give me a review of the command that we can use. I can copy this command and then run it to build the benchmark configuration. As I said, class C with prox equals 8 is what I'm recommending here. And it's going to run through building the different source files with the optimization flags, with the OpenMP flag. And at the end, it links everything together and will put the object files into the executable. And it tells me that the executable is now in a bin subdirectory. So if I do an ls in the bin subdirectory, I now see that it has built this executable here. If I cd into that bin directory, I'm now in the directory where I would be ready to run it. You provided in the tarball a set of job files. There's actually one directory up in the Archer subdirectory. We'll use the one just for running it as a starting point. So copy that into the bin directory, and we can take a look at that. We can execute it, but since we have things set up with a queue reservation, I would need to uncomment the first line of this. That's the reservation for today. if you don't do if you unqueue the wrong one, it'll go into the queue for tomorrow or for Thursday. Probably it won't run very quickly. Or if you don't use a reservation, if you're using your own account, which doesn't have access to the reservation, it'll run through the normal queue, but it might take a little bit longer. We see in here that we're selecting 2 compute nodes. We're saying that we need a maximum of 10 minutes. Should run in well under 1 minute, so 10 minutes is just to give us a little bit of excess here. We're using the training account, and we're using the short queue with the reservation here. We're setting the environment we're going to run in here by switching to the appropriate module. We're again CDing into the directory where we're submitting from. And then again, we have a few more things here which are controlling the setup of the benchmark as well. Telling it we're going to be using 6 OpenMP threads for each of the processes, which executable we're going to run here, which is just the class C with 8 processes here. And then we'll be running things with this ap run command. Ap run is the Cray version of MPI exec or MPI run, which you may be familiar with. Specifying the number of processes, specifying the number of cores we're going to reserve for each process, in this case 1 core per thread, and then the executable, and then after this we could specify any runtime arguments that the executable might require as well. So those are a little bit unusual for Archer Cray systems if you're familiar with other Cray systems, but if you use the provided job script, everything is set up for you, and that's a basis for converting things if you were to run your own application. As I said at the top, it reminds us, submit it from the bin directory, which is where the executable is located, with this qsub command. So I'm going to save that and then just submit it into the queue. If I do a qstat and see what I have in the queue, it's showing me that it's in the queue. We're waiting for 2 nodes. We're in this reservation, so hopefully it'll start fairly quickly. It's now running, and it should run for, as I said, a minute or so. It shouldn't run for any longer than a minute. And then when it's finished, we'll see the output is put into this directory which we're running from. Still running. Now it's finished, so there's no longer an entry in the queue, and we see that there's a new file produced, which is actually the output that the job produced. So that you can direct this into whatever file you want, but that's the name that we gave it with the job name. And in this, we're actually seeing just an echo command that it ran, 8 processes with 6 cores reserved for each process, running OpenMP 6 threads per process. We're seeing this as the output as it was running with the 200 time steps. It doesn't report every one, it reports every 20 time steps. And then at the very end, it has a nice check to verify that it actually run correctly. So this is checking the residual and making sure it's within the expected tolerance. It echoes that this was successful. That's good to hear. And then it also reports how many seconds it took to execute. In this case, 19 seconds. When you run it, the number is probably a little bit different, but it should be within the range 15 to 20 or so seconds, and that's a confirmation that it's running correctly. If it runs more slowly, it probably means that the configuration isn't set up or that you have compiled a different version. So that's a basic exercise, basic steps that you can work through on your own. There's a little bit more than 10 minutes for you to try this on your own before the break. So I would suggest that you might want to try this. If you have any questions, then send them chat, or we'll open up the microphone so we can hear how you're getting on. We'll have a 30-minute break after that, and then we'll continue with the next set of presentations. So it's a good opportunity to make sure that you can build and run things yourself as shown here. So if any of you are having problems connecting to Archer, then that's definitely the first thing that we'll need to resolve. And I think that David or someone else can perhaps help there. If you're already logged in and able to untar and build those, it shouldn't take very long, even if we're all doing it together. It should take just a few minutes. Let me know if anything is different from how I've shown it or how it appears on the slides.
So Brian, I just wanted to check you were seeing any chat messages. I just sent you a silly chat message about your editor, but I don't know if you saw that.
I saw that, yes.
Fine, good, that's fine, no problem.
I haven't seen any messages from anyone else though, so I'm not sure if I can see here everything that's running in the reservation or everything that's, I guess the short queue is probably the best. Maybe I would only see my own jobs anyway. So I see a message from Geert who's asking about screen or tmux. I've certainly never used those on Archer. The best thing to do would be, oops, that was probably not what I wanted. I think module list is usually the best way to figure out, sorry, module avail will show you what other modules that are available in the system. And then you have to look through that and find out if screen or tmux isn't found by default on the path, then it might be through one of those modules. I'm not sure which one it would typically be in. On the default path. So when it comes to editing the job files, you should probably find that you'll have VI or various versions of VI available. Emacs is certainly available. I think it's available by default. Oops, just probably by default I should find it. I'm not sure what other editors there are. Those are the basic ones. So I see one of the instructors is able to run things. This is a different reservation, so it's not someone from the class. There's no worries if you don't if you're not set up and able to run things yourself. It's just it makes the workshop a lot more interesting if you get a chance to try out the tools and see how things work yourself, if not with your own application, with one of the provided applications. So I think we'll be heading into a break. If there are any questions, then you can put them into the chat, and I'll monitor that over the break or during the next session while the next presenters are presenting. Is there anything else that we need to cover before going into the break? Any more general questions? Okay, so I'll finish here and sign off, but as I said, I'll be monitoring things for when we continue. So bye for now.